Well, in this case, let us have a continuation. This time we are going to be focusing with what we refer to as the compound bars. The compound bars, they are now considered two, three, and so on, but they can be placed in parallel or they can be placed in series. So in this case, we're going to be working with bars that are connected, that are placed in a parallel combination. Let's say we've got A and B. These two bars, they are in a parallel combination. And what's going to happen with A and B is that they will be placed at a certain force, which will be affecting the two. Meaning to say we're going to consider the force that is going to be at A and also the force that is at B to give us the total force. In a better view, we can consider these two bars this way. Let's say we have got something like this, guys. I'm just going to try and draw. You see, these drawings, guys, are not for us, as we are into these calculations, mathematics. So I'm just going to try and have this. Maybe you understand what I'm trying to say. So let's say this is what we have. There are two bars that are in parallel, A and B. Okay, let's say I've got A and B in that manner, or you can just have A and B that any way that you want. All right. There is an extension that is going to happen from A, also an extension to B, as we can see, because these two bars are in a parallel. The extension that is going to happen between these two is definitely the same. The extension that you are going to have, which is the change in length, is going to be the same. And considering their lengths, the length of what is representing that of A, and that is what is of B, the original length, it's going to be also the same because these two, they are in parallel. So you'll find out the length of A will be the same as the length that is at B. Same as the extension. The extension of A is the same as the extension affecting B in a parallel combination if the force is being applied and considering this to be our total force. So that is it. That is the only condition that has happened. So in parallel, we can conclude that. Therefore, in parallel, we can conclude that one, the force is the total of the two because A has got its own and B has got its own. So Ft representing the total force is equal to the force at A plus the force that is at B. In parallel, we saw that their extension is the same, so therefore the total extension is equivalent to the extension that is at A, the change in length at A, or the change in length at B, whatever that you calculate. It is going to be the same. And we also saw that the length is the same. The length at A and also the length at B is the same. So with this, we are going to have different values of the Young's modulus of elasticity. At A, they are going to give you the modulus, the Young's modulus. At B, they are also going to give you the Young's modulus. They are going to give you the Young's modulus there. But with these two, remember they are the same, the change in length. So you just want to make some adjustments on this formula. This is what they will give you. And with that, you are the one who is to make adjustments. Out of these formulas, what adjustments can be made? Let's start with the change in length. Before, on our introduction, I said the change in length, as we manipulated, we ended up with the force times length over area times the Young's modulus. Remember when we made those adjustments, this is what we ended up with. With this formula, we also had the part where we can also use the stress, force, the stress and the length over E. You can work with that, which is fine. But I want us to consider this, the basic one that we are used to, so that we do not have a lot of changes. Let's work with what we are used to. So if we are saying these two, they are the same. So from the change in length, let's work with that. Let's work from there. From the change in length. We are going to notice that these two, they are equal. So if they are equal, it means we are going to equate their equivalent formulas also. FL, that is the force times the length area times E. This is at A. So at A, we're just going to use the letter A to indicate that that is A, like that. Or you can use 1 to say this is object 1, this is object 2. So you can use 1 and 2. It's up to you the way that you understand. At B, we're going to use the same thing. Force times length over area times E, which is our Young's modulus. But this is at what? At B. So this will be F at B, L at B, area at B, Young's modulus at B. But remembering that LA is equal to LB, that their length is the same. So you can divide because the length are equal. The length at A and the length at B, they are equal. So these two, they can cancel. And what is it that you're going to remain with? You're going to remain with this formula now, FA. Okay, so this is what you're going to have. FA, AAEL like this is going to be equal to, this will be FB, area at B, the E at B. Nothing is the same there. So because these are mathematical calculations, guys, manipulations should play a role. You can even express FA in terms of what? You can even express FA in terms of FB if it's possible in your calculations. So that can even help you to calculate even the forces, whatever that you have with the total force that we had before. And with these calculations, sometimes they might even ask you to calculate or to determine the stress in each material. This is not going to change, the stress in each material. Our calculations for stress, they are not going to change. In A, the stress at A is going to be force. Remember, force over area. So we need the force at A over area at A. The stress at B, the force at B over the area at what? The area at B. So that cannot change as long their areas are there. As long their areas are there. So we want to check how questions are going to be given and how can we relate this information to solve questions of these bars that are connected in a parallel, like what we're given here. Rods A and B of length 30 millimeters. So the moment that the length is the same, you know that this is what? A parallel. These two, they've got same length. So that is A and B. So A is for the aluminium, B is for the steel. Are placed in parallel. There we are already told that they're also in parallel according to that. So no problem. Then the force. So let us just try to take our information according to what we are given there. So they have the same length. Remember, like I said, if you consider the length here is the same. A and B, they're in parallel. So the length at A being the length at B is given. They have a length of what? 300 millimeters. Just divide by 1,000, 0.3 meters. A tensile load of 75 acts on the compound rod, the wall of it. That is the total force. So the total force is given 75 kilonewton. The rod A is made of steel and has a cross-section of 400 square millimeters. This is rod A. This one is made of steel. So A is representing the part of what? Of steel. So the area at A, which is the area of the steel, is 400 square millimeters. Remember to convert to square meters. You multiply by 10 to the exponent of -6. So it's 400 times 10 to the exponent of -6 in square meters. And that for B, which represents the aluminium, is given. So the area at B is 900. That is the rod B aluminium is area 900 times 10 to the exponent of minus 6 in square meters. We've got there. Areas. There are different areas, remember? Given the stress in the two bars. All right, so calculate the stress in the two bars. The stress in this and also this one. So they need you to determine the stress at A and also the stress at what? At B. And their change in length. Remember, it is a parallel. So the change in length is the same. That is the one at A and that is one at what? At B. They want you to calculate that. Given that E for steel, remember steel represents A. So we are given that. And for aluminium, which is B, we are given their corresponding Young's modulus. All right, so let's see. What can we do? With understanding that we have from these formulas that we had before, these stresses in each material, they need us to have a force and an area there. Force and area. The areas are there if we are to consider from our calculations. Remember, the stress at A supposed to be force over area. So it's the force at A over the area at A. The stress that we're going to have at B, the force at B over the area at what? At B. So the areas, they are there. They're given. But the forces, they are not there. The force at A and that force at B, they are not there. These two are not given. We are just given their total. So meaning to say you're supposed to think about calculating these, determining these forces. So let's think of calculating FA and FB for now. What can we do? How can this be calculated? All right. Remember the total force. There's nothing that we can get from there. Is the total force? It shows us that FT is equal to FA plus FB in what? Parallel. And FA is not there. FB is not there. FT is there. We are given. So we are still going to be lacking from this formula. So is there any formula that connects the force? Yes, it is there. Remember from this relationship that we had where we ended up canceling from XA being equal to XB, we ended up with this formula. Okay, let me write it because there is force there. Remember from what? From the extension. XA is equal to XB. We ended up with the force times length over EA or AE, depending on the way that you want. Okay, let me not change so that we do not confuse each other, guys. We end up like, why is he changing the formulas now? All right, this is it, like what we had before. The one at A, which is our aluminium, which is our A, remember, A, according to us, is representing what? The steel. You can write steel there, you can write aluminium. It's up to you guys. We can just write these letters. There's no problem so that we do not have a confusion. So remember, the length is the same in parallel. Length A and length B are the same. So they ended up canceling these two. So if you check, guys, we have the area at A, we have E at A, the area at B, we have E at B. We do not have FA and FB. So what we can do is to write either FA in terms of FB or FB in terms of FA, whatever that you want. So in this case, I'm going to express FA in terms of what? In terms of FB. It's going to be easier that way. So simply, I just need to remove this. So what can I do? I just have to multiply by area at A, the Young's modulus at A. So we're going to multiply by area at A, E at A like that, so that these two can cancel. We have our FA being equal to this now. So it's going to be this times this, meaning to say our answer is going to be written in terms of FB. Remember, there's no substitute for FB. So it is just going to be FB as it is over what? The area at B. The area for B is 900 times 10 to the exponent of -6 times E at B. Remember, B represents the aluminium. So B, aluminium, E for aluminium is 75 gigapascal. So that's 75 gigapascal. All right. Times the E at the area at A, you're given A 400 times 10 to the exponent of -6. Remember from those conversions from square millimeters times what? E at A, which is our A, remember, is the steel. So the E for steel is 210 gigapascal. So that is 210 for steel. 210 times 10 to the exponent of 9. So this whole part here, if you multiply, like you take this here, you divide to this, because it is in terms of FB. FB, there's no substitute for FB. So you just need these values. Take this, divide it to this one. All right? Or just take it as 1 over this times this. Okay? Simplify properly there. Because this is the same as over 1. So it was going to give us FA in terms of FB. Because this one is going to give us a single number, this one as it is. It is going to give us a single number, which is going to give us 1,244 like that, FB. Okay, please simplify this properly on your calculator. So with this, we can see that we have written FA in terms of FB. FA is written in terms of FB. So how is it going to help us to calculate these forces? It is going to help us because before we can have this as an equation, this one. You can just say this is our equation 1. Before we said the total is equal to what? Let's go back to our total from the total of the forces. From the total, we saw that in parallel, the total of the force is to add the two, F at A and F at B. F at A plus the F at B. So if we check here, this is written, the total force is given, remember, for the whole compound together, this compound is given 75 kilonewton, kilo times 10 to the exponent of 3, which is 75,000. So it simply means 75,000 is equal to FA. Remember, FA is now written in terms of what? In terms of FB. So it will be 1,244 FB plus FB. There is no substitute for FB. So it is an equation that you have made. We just take this equation 1 in place of FA, as it is this one representing FA. You substitute where FA is in place of FA, this one. What is it that is representing FA? FA is equal to the whole of this. So the substitute there. By substitution method, remember your simultaneous equations. So you now have an equation which has got one unknown value, FB. There is only one unknown value here to be considered, FB. So with that, you can calculate the value of FB. It's an equation. Remember, this is the same as what? There's a 1 here. So it was going to be 75,000 is equal to 1,244 plus 1. So it was going to be 2,244 FB. Where we need to calculate this, simply divide by 2,244, divide by 2,244 like that. So these two are going to cancel. You have the force that is affecting B. Remember, B is aluminium. So this is the force that is affecting our aluminium. Okay, so that was going to give us 33,422,46 Newton. If we use this, you can even just write it in kilonewton. That is going to be divided by 1,000. It was going to be 33,422. kilonewton like that. So we have got the force at B. With these calculations that we have, guys, all this manipulation from that extension, all this, it is helping us to have one of the forces. So we have that force at B as 33,422 kilonewton. So what are we going to do to find the force at A? We can now use that relationship that we had here, that FA is equal to 1,44 of FB. So it's 1,244 times FB. Which one? The one that you calculated, which is 33,422. It is in kilonewton, guys. So whatever that you're going to get here after multiplying these two, your answer is going to be in what? In kilonewton. Okay, so that was going to give us the force at what? At A. Already there's an equation for that. So just multiply these two. You're going to get 41,577 kilonewton. So this is F at what? F at A. All right. So with the force at A, let's just write this one aside. 41. Remember, this is 41,577 kilonewton. So that is it, guys. We calculated these forces. These are the missing values on our calculations from what we needed to calculate. The missing values were these forces. So that is why we had to calculate FA and FB. After these, we can now just substitute because the areas are already there. So what is going to be the stress in each of these materials? So the stress at A, force at A over the area at A. So the force at A, we calculated these guys. 41,577 times 10 to the exponent of 3 over the area at A. Our A, its area was what? That is 400 times 10 to the exponent of minus 6. Which is this the part, remember, A represents the steel. So this is the stress affecting the steel. Okay? So just like that. Remembering that this is stress, and stress in megapascal times 10 to the exponent of minus 6. Your answer is going to be in what? In megapascal. Your answer will be in megapascal. Whatever that you have, multiply by 10 to the exponent of negative 6. So that was going to give you 103,923 megapascal. That is the stress affecting the steel. B, which is for the aluminium, we can calculate that because the force at B is there. So for B, just gonna a continuation, the force at B is already there. 33,422 times 10 to the exponent of 3. That is the, remember, B is for the aluminium. It's already there. Over what? Area at B, area for that aluminium piece, 900 times 10 to the power of minus 6, converting to the square meters. 900 times 10 to the exponent of negative 6. It's stress that you're calculating. Do yourself a favor, just multiply this by 10 to the exponent of minus 6 so that your answer will be in megapascal. So with this, we are going to calculate the stress at B for the aluminium. The answer that you're getting, 37.136 on your calculator, is now in megapascal. So you have to be very careful with what you're given. Information, you can work this from anywhere. So the parallel combination will be on those length extension. Then you play around, you manipulate, you make FA the subject, substitute this and that. All right. Then another question they want you to calculate is the, remember, their change in length. And I said the change in length is simply the same. X total, you can calculate from A, you can calculate from B, whatever that you are given. So in this case, are we having like the force at A? We have got F side, guys. We can use anything. So here, I'm just going to work with 1. Then you guys just use any other part. All right, just choose any other part that you're going to use, guys, and that will be the same. So A is representing the steel. So I'm going to work with A. So that is it, guys. So that is the second question. So X total, I'm going to use XA. So you choose. So I want you to use XB and see if you got the same thing. Remember, X, its extension, change in length. Change in length, guys, does not change. The formula, it's force times length over what? Area times the Young's modulus. So you're talking about at A. So use force at A, the length, original length at A, the area at A, the Young's modulus at A. So that is going to give us XA, which is the total because it's a parallel, in parallel. They're the same. We're going to see another thing when they are now connected in series. Parallel, they're the same. So let's substitute FA. We calculated these forces, guys. I think I removed them, but if you still remember, we calculated the force at A. It was 41,577 kilonewton. If you still remember, guys, that was 577 kilonewton times 10 to the exponent of 3. The original length at A, remember, length is the same. The length at A is the same as the length at B, so use the 0,3 meters as it is. Over what? The area at A already given. 400 times 10 to the exponent of minus 6. Then E at A. Remember A, our steel. Okay. So what is it that we have for the steel? The E is 210 gigapascal. So we have that E at A, 210 times 10 to the exponent of 9 gigapascal. So that was going to give us the extension, change in length, the total of it, of the whole part, 0,000148489 something like that in meters. So you can just write this in a way that you understand. Since there are so many zeros here, you can avoid to use millimeters and just like use a power 1, 2, 3, 4. You can even up to this point. So this can be written as 1,485. This one is going to change into a 5. So it's 1,485. All right, which is times 10 to the exponent of what? The commas that we moved, but with a negative. So you can have it that way. That is our X total. Total extension. According to what we are given, that is going to be our total extension. So this parallel combination, guys, is just one and the same part that you'll be given, whether the questions are presented this way or other way, it's going to be the same. There they are giving us that this is a rigid beam. On another example, a rigid beam hangs from 3 wires. There are 3, each 3.5 meters long. 2 outer wires are made of bronze. There are 2, take note. The 2 outer wires, they're made of what? Of bronze. And the central wire is made of steel. So it's like there are 2, like they're in parallel, but it's like there's a bronze and there's another one there and the one down there. That is what you're given. They guys, they take note, the 3 of them, they're each 3, they have equal length. By just having equal length, to say this is the one for the bronze, another one, another bronze, and the outer one they are saying is what? It's steel, like that. To have the same length here, it means these 2, they will be in parallel. They cannot have the same length if they are not in parallel. So having the same length, it means this combination that we are given here is connected where it is in parallel from the same length. Same length. It cannot just happen there. Definitely going to have same extension. So they are given, there are 2 bronze. So here, meaning to say in terms of the area, I'm going to multiply by 2 because there are 2 of them. The horizontal beam is placed under a load of 3 kilonewton. The diameter of each bronze is given for the bronze and the diameter for, so as you can see, we're not even told that this is in parallel. So where do we get that? From the length. That is where we can tell that these two are in parallel. So what about the term rigid there? A rigid, that is something like unable to bend or to be forced out of shape, unable to be forced out of shape. So there's nothing important about that in this case, all right? So let us consider our information. As we can see that just one or two things to consider. Our length, we are given for all of these. So the length is equal to 3.5 meters. Remember, length is the same for the bronze, for all of these. The outer wires are made of bronze. The two outer, two of them. And we are given the horizontal beam is placed under a load of 3 kilonewton, which is the total force. That is our total force. Is given as 3 kilonewton. The diameter of each bronze, 4 millimeters. So we are talking of what? The bronze there. The diameter, considering the bronze, is given as 4 millimeters. That's divided by 1,000, guys. That's 0.004 meters. But remember, they are each, so they are 2. So in terms of the area, you're going to multiply by 2. Take note about that. Then the diameter for the steel, this one for the steel wire is 3 millimeters. So the diameter for the steel in that case is 3 millimeters, which is 0.003 meters. Then we are given E for steel and E for bronze. Those ones are given. Calculate the stress brought about in each wire. So just like the previous case, there's nothing that only the part of the area there. So as we saw previously, that the stress brought in each condition, if you're considering the steel, it is supposed to be from the force over the area. The force of what? Of steel over the area of steel. That is it. Considering the part of the bronze, the same thing. Force over area, stress. So this is the stress for the bronze, considering the bronze. So you need the force for bronze and the area for bronze. Just like that. So you can even use 1 and 2, A and B, as long as you understand what is it that you mean there. But nothing has changed, guys. So let us consider our areas, because as you can see, the areas this time they are not given. The forces are also not given. So unlike the previous case where you're given the area, this time you are not given. So you need to calculate the area for steel first. And so let's talk about areas first, because the diameters are there. So calculating areas, let's start with the bronze. Okay, so the area for the bronze can be calculated. Remember, area pi d squared over what? Pi d squared over 4. But this we are considering to say there are 2 bronze. There are 2 of them. So it's affect to say whatever that you're going to have is going to be times 2. So that's pi times d for bronze in meters, 0.04 squared over 4 times 2. All right, so that was going to give us the area for bronze in that case. If we multiply by 2, that's a lot there, guys. 0.0000 2513274, something like that in square meters. So you can just write this as the area for bronze is going to be, let's try to move our commas, 1, 2, 3, 4, 5. Let's just target a 6, guys. 5, 6, because there are so many zeros here. Let's just target a 6. Okay, so it's going to be 25,133. Okay, so that was going to change, the 7 was going to change this into a 3. So that's 133. Okay, 25,133. Okay, that's the 6. 1, 2, 3, 4, 5, 6. Like the zeros that we have. Okay, if you want it to have it that way. Or you can have it in terms of the numbers. like this. Okay, can have maybe, I might confuse you guys to say maybe you are used to those whole numbers just to target a whole number. You can just target a whole number like this. You move on to 5, like 1, 2, 3, 4, up to here, 5. Okay, so that I do not confuse you guys to say you were targeting a whole number this time. What? Okay, just maintain whatever that you want. There we moved 5 commas to the exponent of minus 5 square meters, or you can just have a 6. It's up to you. So that's the area for bronze. All right. So you do the same thing for the area for the what? For the steel. So let me just write it here, guys. We calculated because we're going to have a lot of things there to calculate. 2,513 times 10 to the power of minus 5. Let's move on to the steel. Remember the bronze, there are 2. So steel is not affected. It's just 1. Steel that we have there is just 1. So its area was going to be taken from what? Pi d squared over 4, which is the diameter of the steel to be used. So that's pi times the diameter for the steel, 0, 0. All right, that was going to be 0. Okay, let's hope, guys, this is not going to affect again. If we check, that's a 0 there, 0.3 squared over what? Over 4. So it will give you those decimals again, just like the previous case, 0, 0. Yeah, there were so many zeros. I think there were 5. There was 5, 7, 0, 6, 858 square meters. So you can just use, 1, 2, 3, 4, 5, until we get a whole number, 6. So that will be 7, 0, 6. This is going to change into a 9. The 5 is going to change into a 9. So that's times 10 exponent of negative 6. All right. So if we knew, guys, we could have just used a negative 6 there on this one, but no problem. Just use whatever that you want, guys. That is the area for steel is given as 7,069 times 10 to the exponent of minus 6 in square meters. So you have calculated your areas. They are there. They're still there, guys. On these formulas, the areas we have, we are now left with the force. So where are we going to obtain the force? That is where you ask your question now. The forces, as our previous question, we saw from the extension formula, because we do understand now we have to find forces. That is FA and what? FB. So we saw that in the previous case that they were taken from the extension in parallel. The extension is the same in parallel. The extension is the same. X for A and B is the same. So the extension that we have for steel is same as the extension that we have for what? For the bronze, the change in length. So this extension from the formula, guys, we saw FL area times E, gonna have the same FL area times E, but this is just to say this is for the steel. Okay, so they are just considering to say this is for the steel. And this other part is for what? Is for the bronze. Okay, this other part is for the bronze, just like that. So if we were to consider that concept again, that the length is the same because they were in parallel. The length is the same, so the length for steel and the length for bronze is the same. So that part was going to cancel. And we saw that we can manipulate and make one the subject to another. You can make F steel the subject. You can make F bronze the subject. So in this case, I'm just going to make this the subject. So I'm going to multiply by the area of steel in this case, and the E for steel in that case. This part I'm going to remove with this. So I have to multiply with it the other side, meaning to say the area for steel, the Young's modulus for steel. So these we're going to cancel. You have the force representing the steel from this, written in terms of that force for the bronze. That is the only condition. So these ones, we calculated the area, Just going to substitute now. Area for bronze, remember, we calculated this 2,513 times 10 to the power of minus 5 times the E. For bronze, you are told, you're given before, the E for bronze, 90 gigapascal. So that is 90 gigapascal. 90 times 10 to the exponent of 9 times this part. The area for steel, we calculated this. The area for steel, what is it that we got? 7,069 times 10 to the power of minus 6 times the E for steel from our information. That's 207 gigapascal for steel. We are given that 207. Okay, so it's just a repetition. 207 times 10 to the exponent of 9. This is the same like over 1. So like I said, you can just use your calculator, simplify this one over this one. So it is going to give us a certain decimal in terms of this phosphor bronze, because you cannot calculate that. So that is going to be 0,647 times the force affecting what? The force for bronze, like that. So this is where we are. It's an equation, this one, which relates two things. So what are we going to do with this relationship? We saw in our previous case that we must use what? The total, because in parallel, these forces can be added to give us that total force. So from the total force, we can now determine these together. So this we can even write as equation 1. Then from the total force, Ft is equal to the force for steel plus the force for bronze. So we have that one. The total force is there. 3 kilonewton, 3,000. So 3,000 is equal to these two. Sum, but we are given now F steel. We have written this in terms of what? F bronze, which is 0,647 F bronze, like that. Plus that one, which we do not have the substitute just as it is, just like FA and FB, the one that we had before. So what is that we can do? We can solve for this FB for bronze. We can calculate this, just like what we had before. This is an equation, guys. This is a 1. So it means 3,000 is equal to 0, this plus 1. That's 1,647. So we need the force affecting the bronze. So divide by the decimal, 1,647 both sides, 1,647 both sides, just like that. So this was going to give us the force that is affecting the bronze, which is 1,821,494 Newton, right? Which you can convert to the kilonewton, or you can just leave it like that, guys. We have worked with a lot of things. Let's just leave it this one like this. So with this one, now we can determine the force of what? Of steel. Because it's taken from this decimal that it's 0,647 times the force for what? For bronze, the one that we calculated here. 1,821.494. The product of this is going to give us the force for what? For steel, which was going to be 1,178,507 Newton. We calculated these forces now. With these forces, those extensions, those values for the stress can be obtained for each. Remember, guys, all this, okay, let me guess. All these calculations that we are doing here to manipulate, find this and that, it is because we wanted these forces for steel and for bronze. Now that we have them, it means these extensions, these values for the stress can be calculated. So the stress affecting the steel is going to be the force that we obtained for the steel. Remember, it was 1,178,507. You divide to the area for steel, the one that you got here. Remember, you calculated this. So they will give you all these guys just for you to manipulate this and that. That is engineering for you guys. Anyways, so to the megapascal times 10 to the exponent of -6, your answer is now in megapascal. So that was going to give us 166,715 megapascal. We have a solution there. We move on to the one for the bronze. So we saw that for the bronze, we need the force that is affecting the part of the bronze, as we had the force for the bronze, guys. Remember, it was 1,821. This one, we got this. Just gonna substitute into this part. So let me just even remove this, guys. There's no need. We're done with this part. So you're gonna substitute this. We've got the force for what? We've got the stress affecting the bronze. So the force for bronze, remember, it was 1,821.494. We calculated this over what? The area affecting the bronze, 2,513 times 10 to the power of -5. To the megapascal times 10 to the exponent of -6. Your answer is in megapascal. So that was the condition. That was the condition. Your answer is now in megapascal. So let's substitute this, calculate, multiply times 10 to the exponent of -6. You're going to get something like 72,483, which is now in what? In the megapascal. So that is, our formulas can be very, very useful. Let's do revise as much as we can. All right. Let's move on to another part. Calculate the extension. Why are they saying just the extension? Because that extension is the same, remember. Extension is the same. So, and as I say, that extension, since it is the same, we can use any part. Since the extension is the same. And we can even use any formula that you know for extension. The total extension in a parallel combination is the same. Is the same as that extension that is happening for steel. It is the same as that extension that is happening for bronze. So you just choose whatever that you want. So in this case, guys, I'm going to work with one part. Just going to choose which one. With force that I'm having, just going to work with any of these. So let me just take this one for bronze. I can even use the one for steel. All right. What was the force there? You can just use that one for steel. Remember, the force here for steel, we calculated this. All right. So just use any part. You can even use the part where you are having where you are working with the stress. Remember, there's a formula that stress is used. All right. So I'm just gonna use steel in that case. Remember, the force for steel, when we calculated, we must remember the force, it was 1,178,507 Newton. Just use the one that you want. You can even use the one for bronze. So using the steel, what is going to be our extension? And that extension is the total one for the whole part, since it's a parallel combination. So for steel, the force times length over area times E. This is for steel. We are given this. So it is just a matter of substituting into the formula. The force for steel, this is 1,178,507 times the length for steel. Remember, the length is the same. In a parallel combination, the length is the same, 3,5. So we are going to use the same length given there, 3,5. Then we are given the area. We calculated, remember, this we have it. Area for steel, 7, this times 10 to the power of -6 as it is. 7,069 times 10 to the exponent of -6. Okay, times the E for steel, the Young's modulus for steel we are given, which is here for steel 207 gigapascal. 207 times 10 to the exponent of 9, that is gigapascal. Remember, this is extension. The value that you're calculating is in meters from this part. So this extension was going to give us 0.002818849 in meters, which we can convert now to millimeters from there. It's up to you now. You can convert this to millimeters times 1,000 because there are a few zeros there. So times 1,000, your answer is in what? Millimeters. That was going to give us 2,819 decimal places. So that's our total extension that we are given there. From where? From one of these. So you can use part of bronze. So I want you to use that. Try it, calculate, and see what's going to happen. And in this case, on the C, they are saying discuss why the beam stays horizontal. Why would this not work with one bronze and one steel wire? Why is it like they stay horizontal? The beams stay horizontal because the outer wires are made from the same material. They are supposed to be same material so that the shrinking part is not going to affect. So these are within same length, same material used on that outer surface. So guys, let's do our revisions as much as we can. Then we're going to meet again in another class working with a series combination, as we saw that there's a lot of things there. Again, in a series, we're going to see that there'll be a lot of things to consider. So just try to revise. This is now your mathematics involved, your formulas involved, manipulations, this and that. And it requires time. As you are working with this subject, you need time. So just try to build time for it. Everything will be fine. Till we meet again.